That roof is on fire. We gonna take it high. So in our last session, we were supposed to add the components because we have found the three forces on one charge. So let's just do that. So we are going to add F3 and 1 plus F4 on 1 and then F2 on 1. What is F3 on 1? This one. Hello, Adna, are you here?
Yes, I am.
Okay. So what's our X component? You said you're going to add the X component first.
Yes.
Okay.
And then I added KQ squared over L squared plus KQ squared
KQ squared over
2 over root 2.
I think I started with this one. Which is this one?
Yes.
Yeah.
2 over 2L squared. And then I took out KQ squared over L squared as the common factor, and then as an HCF, and then I put in a bracket 1 plus 2 over root 2 bracket.
Before we move on, let me go back. We only have two components in the X from these three forces.
Yes.
Oh, because one of them was just in the X and the other just in the Y. All right. Thank you for reminding me. Yeah, and then you took what?
KQ squared over L squared out.
KQ squared over L squared, yeah.
Bracket 1 plus 1 over 2 root 2.
1 over...
No, 1. Just 1.
What am I doing? Okay. Remember, there's a negative here. I didn't hear you mentioning it.
Because I drew my free body diagram wrong.
Okay.
So then my X direction was in the positive instead of the negative.
I remember now. So our net force in the X direction is KQ squared over L squared of 1 over negative 1 over 2 root 2 plus 1. What's the value? Simplified.
Newtons. Excuse me?
The value, what's this value combined? Simplified.
Oh, I didn't do it. I just did that. I left it as is, and then I did the final answer into decimal.
Let's simplify this. We need to simplify it. I think it can be more simplified than this.
$1.354.
Are you sure?
Oh no, my bad. I added instead of minusing it. It's negative 1.35. No. I'm so sorry. 0.
Yeah.
0.646.
And then the net in the Y.
Oh, it's the same as, since it has the same components, like F1 equals to F2 and the F3x equals to F3y. I just wrote the answer, the same answer.
They're the same.
Yeah, the F1 the x component of f1 and the y component of f2 is the same if we look like back at our calculation, and then the f3x is equal to the f3y.
Okay, I think this is one. You're saying you took this one and then this one and you realize they're the same. They're going to be different because of the signs. So let's just repeat it. That's kq squared over L squared plus kq squared over 2 root 2 L squared, and then you take out the kq squared over L squared. You are left with 1 plus 1 over 2 root 2, which is kq squared over L squared multiplied by
1.35.
1.35.
Yes.
Okay.
1.35.
Okay, so the net force then is going to be, we can also take this as a common factor out, and the components are going to be 0.646 I hat plus 1.35 J hat. Are there any questions on this one? I think it's finished right now, is it not?
Yes, you just have to find the angle.
Oh, all right. So to find the angle, what do we do?
Theta equals to arctan Fy over Fx.
Fy over Fx. Which is arctan of what component?
Kq squared over r squared.
I think let's just take the components. Remember, the magnitudes are going to cancel. Like if we come here, these are our components. These are the only things that matter right now to find the angle, the y over the x. Because these two are the same for the x and the y, they are just going to cancel. So theta is
64.43 degrees.
64.4 degrees.
We could just scroll back up to Sir's free body diagram.
Yeah.
Why did we minus our x direction, our x components, if its direction is both to the left?
Here.
Yeah.
Remember we came here and said if we are going to focus on Q1, F1 on 2, I mean Q2 is going to push it's going to push Q1 this way, right?
Yes.
And then, okay, from this one, I think it's this one that gave us another component. This one is also giving us another component in the X because it's diagonal. It's pushing us to the left. So we are refining our positive S to the right. Now if it's pushed to the left, our force is negative.
Okay.
And then it's pushed upwards by this one downwards, and it's also pushed upwards by the component of this one. So upwards is positive on our diagram, therefore our y is positive but our x is negative.
Okay.
Alright.
But I still don't understand why. Okay, I understand. Thank you so much.
You understand?
Yeah, I see where I went wrong.
Alright. Are there any questions, guys, before we move on? If there's none, okay, let's move on to the next question. 21.64. Okay, I think there's a question that we skipped. 21.58. Who is responsible? Sorry. We said on our next session, we are stopping with the exercises and we are starting Gauss's law. And then each time when we meet, we do questions, maybe one or two questions, and then continue with Gauss's law or the topic that we will be covering for that day. This is to make us balance, let's not be behind. I want us to be in sync with your lecture. Is that okay with everyone?
Yes, sir.
All right, thank you. So allow me to do what? To open another slide. And from now on, I won't be adding any new notes on this slide that we just closed. I'm going to send you that PDF so that you can read it like your notes. You can remind yourself of what we did before. So I'm going to download this out of here. Welcome to Spark Tutorials. I'm still your lecturer. Our next topic is Gauss's law, and Gauss's law is intended to make things simpler for us. You'll find that with Gauss's law, we are just going to look at the symmetry of our problem and then calculate using shapes. We're going to mostly use shapes here to simplify stuff. So our learning objectives are: how can you determine the amount of charge within a closed surface? So we are going to use surfaces to calculate the electric field, and you'll find that the charge enclosed by some shape that you use will have to be equal to the electric field. And then you're going to find that, okay, another learning objective is that you need to know what flux is and how to calculate it. And then relate Gauss's law with electric flux through a closed surface. And then calculate electric field using Gauss's law and symmetry of the charge distribution. And then also you have to be able to find a charge on a conductor, on a charged conductor. I hope this is going to be helpful when you revise. So our notes are very simple and straightforward. If you have a charge, you can think of an imaginary box, and in that imaginary box, this box doesn't really exist, but you need to imagine it. So you draw a box around your charge. You draw a simple shape, one that is simple to calculate its area, and one which is proportional to your charge. Right now our charge is circular, so a circle is proportional to most shapes. But if you find that you have a shape like this, it's better to use an imaginary surface like this to find the electric field rather than to use a circular one. This one is harder, this one is easier because there are already having the same shape. So that's what's gonna happen in this topic. Now, as you can see, if our charge is positive, the flux, the electric flux, you see those arrows, we call them the electric flux. So those fluxes are radially outward if it's a positive charge, and they are radially inward if it's a negative charge. Yeah, this is a negative charge. And the magnitude of the charge is equal to the flux. It is proportional to the amount of flux coming out. So this is two more charges. You can see there are more arrows. The same thing happens with a negative charge. The more charge is enclosed, the more flux comes in. We also have to know conditions on which there is no flux. Whenever there's no flux, there's no electric field. So if there's no flux, that means there's no charge inside. But in other cases, there are charges inside, but the charges are equal in magnitude but opposite in signs. So they just cancel. Flux in is equal to flux out. It's like having a bottle which is having a hole at the bottom. You pour water from the top, it comes out at the bottom. So there's no water inside, meaning there's no electric field that's coming out, because the electric field going in is coming out. They just cancel. Another case is whereby the charge is not inside, the charge is outside. So this charge, if it's positive, it's radially giving out the electric field, and then you draw a shape here. So this is flux in, flux out. So there's no electric flux in this box. Is this clear, guys? So far? Hello?
Yes, sir.
Alright, and then in this case, I think this is the repetition here. This is repetition of what we just said. What we can see on this one is that if you double the charge, the flux also doubles. But if you double the shape, the flux stays the same. And you want to know why is that the reason? When you double the shape, it's similar to saying you want to find the flux, but okay, let's take the bottle analogy again. If you use a larger bottle, you use a larger bottle, but then you don't change what is inside. What's coming in is equal to what's coming out. Just because the bottle is larger doesn't mean there will be more water coming out, or there will be more drink coming out. The drink doesn't change, the charge doesn't change. So the charge is the one that dictates how much electric flux comes out. It is even explained mathematically here below the diagram that if you increase the area, if you increase your shape, let's see, each dimension, let's see here, if this is now twice this dimension, you also have 2 times this dimension, which means now our area is now 4 times as large, 4L squared. Here it was just L times L, it was just L squared here, but now there it is now 4 times larger. You see, it is now 4 times larger. But look what's gonna happen when you calculate the electric field. Remember the distance. You're going to say the distance is For this one, the distance is L. So you're just going to say L squared. Remember KQ over R squared. When you calculate the electric field, you're going to say this is L squared for this part. But for this part, you're going to say this is KQ over 2L squared. 4L squared. Now do you see that these two are going to cancel? This 4 and this 4. They are going to cancel. Why are they cancelling? Let's discuss the formula for the flux so that you understand. The formula for the flux says electric field times area. So you take the area of 4L squared, you multiply it by the electric field of KQ over 4L squared. This cancels, you are just left with KQ. The same thing that happens with this part. Before you change the dimensions, you have the area as L squared, you have your electric field as KQ over L squared. The L squareds cancel, all that is left is KQ. So as you can see, increasing the dimensions doesn't change the electric field. Is this clear?
Yes, sir.
Right. So to summarize, we need to look into special cases. And these special cases say whether there is a outward or inward electric flux through a closed surface. It depends on the sign of the enclosed charge, like whether it's coming in or out. When it's positive, it's outward. When it's negative, it's inward. Another one is the charges outside do not give any net flux. So that's what we saw. If a charge is outside and this is your shape, flux in, flux out. The net flux is 0. The other case is whereby you change the dimensions. So this one says the flux is directly proportional to the amount of charge enclosed. And it is independent of the size of the surface. So this says even if you use a smaller or a larger one, it doesn't matter. It doesn't matter. The flux is still going to be the same. The electric field is going to be the same. Alright. So we are done for this part. Now let's move on to something else. The formula for electric flux I carried by mistake. EA. This is our flux. So this is going to also repeat what we just said. This is your area. Let's say this is your sheet. This is your surface. Flux in, flux out. So flux is 0 because it came in and went out. But we can calculate how much flux passed through, not how much flux is inside this shape, because it came in and came out. But we can calculate how much flux passed out. Now to find how much flux passed out, we are going to say this formula can also be written as EA cos psi. And as you can see here, because the angle between, okay, this is what we need to know. In order to calculate the flux, we are going to take the angle between the electric field and the normal to our area. So the normal is what is the normal, guys?
It's that area vector.
The area vector. It's perpendicular to the surface. So if this is our surface, this is our normal. Now, the electric field and the normal are in the same direction, so there is no angle between them. Now, what is cos of 0?
It's 1.
It's 1. Meaning now our electric flux here, the flux that's moving here is EA. So there's flux here and it is at its maximum when the cos theta is 1. But let's look at this case whereby the area is now tilted. In this case, you need to define your normal. Is your normal this way or this way? If it is this way, you're going to do the same thing. This is your normal, this is your electric field. What is the angle between them? But if it was in this direction, you would say, okay, I think this angle is now negative. So to calculate the flux, you would say EA cos of the negative angle. But remember, cos as an angle or cos as a function is an even function. So whether you insert a positive or a negative value here, it comes out as positive. Alright, so we can also evaluate a third case whereby the electric field and the electric flux are 90 degrees. The electric field and our normal are 90 degrees away from each other. Now we are going to have to take the cos of 90. Alright, cos 90, which is 0. Is this clear, guys?
Yes, sir.
Alright, now this is the general formula for the electric flux. When it's now changing, here everything is constant, but what if now what is changing here? It's either our angle is changing or our area is changing. But if it is E cos theta dA, our area is changing. So this is it. So after integrating this, this is what you would have. Electric flux is E dot A. Alright, let's do some examples. Who is in charge? I have a list. And if you Loiso. He's not here. Guys, why are you banking? Why are you banking classes? Okay, we are going to have to do this on our own. Who's responsible? Sorry, who can help us read the question? I apologize for being so distracted. I'm still thinking of this person who just ran away. May someone help us in reading the question?
A disk of radius 0.1 meter is orientated with its normal unit vector n at 30 degrees to a uniform electric field E of magnitude 12 times 10 to the 3 Newton per coulomb. Since this isn't a closed surface, it has no inside or outside. That's why we have to specify the direction of n in the figure. What is the electric flux through the disk?
Okay, let's see our diagram. So to find the electric flux, we would say, oh, I forgot something. Flux of the electric field. You always have to put this E here. We are going to do flux of a magnetic field and you would put B. So they are not the same. It's E A cos psi. So our electric flux, our electric field is 2 by 10 to the 3, 2 by 10 to the 3 multiplied by the area of, it has a radius of 0.1 and it's a disk. The area we are looking for is this one. So it will be just the area of a circle, pi radius squared. Our radius is 0.1, we square it. We multiply by cos of the angle between the electric field and our normal, which is 30. So our flux of electric field, may you please calculate it?
Uh, 54.41.
54.41. What are the units? We have Newton per Coulomb,
Newton meter per coulomb.
Newton meter per
Meters
Coulomb.
per coulomb.
Okay, I was about to derive them. So let me shine, I was already doing something here. This is the area, right? Newton per Coulomb is the electric field, and then multiplied by the area is meter squared. So what did you say the units are again?
Newton meter squared per coulomb.
Oh, it is like this. Oh, all right. And then part B, what is the flux through the disk if it is turned so that n is perpendicular to E? This one is conceptual. What's gonna be our value here? What's our value here, guys? 0. Remember, we now have EA cos 90. Oh, before we do anything, let's read again. What is the flux through the disk if it is turned so that normal is perpendicular to electric field? Electric field and normal. These guys like to trick us. Do you know what they say sometimes? Sometimes they say such that, I need to remember what they like to say. But something is going to be perpendicular, but it's not the normal. They want you to be confused by the perpendicular. Let me go to the diagram. Maybe I will remember. Let me see. They might say such that.
The electric field is perpendicular to the disk.
Yeah. The electric field is perpendicular to the disk. And you'll find that you're going to think, it's 0 in that case. But actually what they are saying, hey, mute your mic. If they are saying electric field is perpendicular to the disk, this is when it's at its maximum, because the electric field and the normal are in the same direction. So this is how they like to treat us. But we already know that they like to do that. They can't do it this time around. Okay, now it's gonna be 0 because the normal and the field now, in this case, they are 90 degrees apart. Now part C says what is the flux through the disk if the normal is parallel? Okay, now when it's parallel, we have EA cos 0, and we know it's at its maximum, right? It is at its maximum. So we are going to just multiply 2 by 10 to the 3 multiplied by our area of pi radius squared. What's the value?
62.83.
62.83 Newton per Coulomb. Why the meters? Yeah. Alright. Are we all on the same page? Alright. Let's move on to example 22.2. Yeah, the owner of this problem is still not here. Ish. Guys, don't disappear on me. It's boring. Please. Are you guys here? I think I got lost. My connection got lost.
You're still here.
Oh, okay, thank you. Yeah, I only got lost on the phone. You see, I also joined with the phone so that I can check what's going on. Alright. Now, this problem is very interesting. Let's look into it. Someone else, may you please help me in reading the problem? I'm now lazy. I'm a lazy teacher. Someone, I'll just call a name that's in my mind. Dineo. Is Dineo here, guys? Dineo.
Yes, I'm here, sir.
Yeah, your name popped into my mind. Yeah, please help us.
But that is not my problem.
Yeah, you're helping me. I'm going to have a problem with the owner of this problem. Me and that person are going to have a problem. So please just help me in the meantime. Hello.
So should I read the...
Yeah. I thought you were on strike. I was so satisfied. I was so afraid.
You were afraid?
Yeah, that you're striking.
No.
Okay.
An imaginary cubical surface on side L is in a region of uniform electric field E. So you need to find the electric flux through each face on the cube and the total flux through the cube when it is orientated with two of its faces perpendicular to E, and then B, the cube is turned by an angle theta about a vertical axis. So when the electric flux, when it's orientated perpendicular, I think it's gonna be it's gonna be which will give us zero.
Okay. Do you want to help me in answering it?
Yeah, I can help, sir.
Okay. So let's see. I'm lost again. Sometimes I get lost. Electric field flux through each face. Okay. So you said when it's perpendicular, which sides are perpendicular to the electric field? N5, because the electric field is this way, so N5 is perpendicular.
N6.
So we can call this surface 5.
Okay.
So let's say on surface 5, did you say 6?
Yes.
And then 4, right?
Yes, sir. N3.
4 and 3. Electric field and normal. are 90 degrees apart. So E, I'm not gonna use this one. I want to dot them. E dot A is 0. Alright. So why do we have the electric field on surface 2?
It's on surface 2, sir.
Yeah.
On surface 2, it's going the same direction as the electric field, so the angle between them will be 0, and because 0 is 1, so it's gonna be plus is equals to the integral of E vector E dot A
dA.
dA, say my bad, I forgot.
Yeah.
And then we can write it using the cosine, so it's gonna be E dot A cos theta.
EA
times
cos.
A cos theta, not dot.
Yeah.
And then we're going to say E. They didn't give us the value of
The value of,
E. I don't see.
we will leave it just as E, but what's our area?
Our area is going to. Can you go back to the statement, sir?
Yeah.
Since it's a cube, it's gonna be, I think, L times M.
Yeah, L times L, which is L squared.
Cosine of 0, which is just 1.
Cos 0, which is 1.
Then our answer will be E L squared.
Yeah.
Yes.
And then on surface, is it surface 1? Yeah, this one that's going backwards. Yeah.
So we're going to say flux.
Flux.
The electric flux is going to be E A cos theta.
Mm-hmm.
So it's going to be
E
L squared.
L
Since the
squared.
area is the same.
Yeah.
And then cos 180, which is negative 1.
Cos 180, which is negative 1.
Yes. So our answer will be negative EL squared.
Negative EL squared. Alright. Thank you. That's
Okay,
part
sir.
A. So we are moving on to part B.
Then should I also have with part B?
Yeah, I think if you think you are still satisfied with helping me,
I'll try my best, say.
alright.
So when the cube is turned by angle,
Yeah, I just
It's
want to
about-
take it. I want to take it to this page so that we can see it well. Yeah, now they turned it around. So just
can
to
we go
draw.
back to the question first date? I wanna add something. I don't know if it's relevant.
Yeah.
So if we add the fluxes for the cube when it's perpendicular to E, the number of the magnitude of the flux will be 0.
Or if we add these two, all these components, in fact,
Yes.
all these electric field due to the surfaces, yeah, it's very important. If the question maybe said, show that the flux is 0 or find the net flux for all these surfaces or through this shape, then you'll find that the answer is 0 because the other one is moving backwards, the other one is moving inwards.
Yes. Sir.
Yeah, flux in, flux out. So we can do that. We can say flux E total is equal to 0. Yeah, maybe I should show why. EL squared minus EL squared 0. Alright, thank you for bringing that up.
Yes, sir.
Now this one might be long. It might be our last problem for today because they tilted our shape, maybe the electric field or our shape, and now what we have is I'm trying to think of the way so that we can all see it from above. This is what we are gonna see from above. It's as if now the electric field, I'm not an artist, but I was an artist back then. Did you tell us how much minutes are left? How many minutes are left?
11 minutes, sir.
Oh, I thought someone talked in the background and telling us. So this is now the case. And if we drew this box again, just to show, we can see now that upwards, remember we have the normal upwards, right? What's gonna happen? And the normal downwards. What's gonna happen for these two cases? These two are still in they are still perpendicular to the electric field. So we can say up, no, not up, top. English was not my first language. Top and bottom surfaces are in fact have n perpendicular to electric field. Therefore, flux of electric field is 0 because they are perpendicular, right? However, if we then look into these ones, this one that's moving in this direction, there's an angle here. If you look into this one that's moving in this direction, there's an angle here. It's a normal. It's a normal. If you look backwards, there's an angle here and it's a normal. If you look in the other direction, this is a normal again and there's an angle here. Did we leave any normal, guys? Do you think we left out any normal?
No, we didn't, sir.
Alright, thanks. So which angle are we given? We are given this first one. They are saying this one is theta. And we'll just have to figure out the other ones. How do we figure them out? If we do this and this, these ones are cancelling. Alright, in fact, we don't have to be so worried. This is 90 degrees, right? So this means this one is 90 minus theta. Not psi. This is 90 degrees. It's similar to drawing on top of this box. Like if you draw something like this is 90 degrees. So now we need to use the angles that we learned in high school. When the angles are doing this kind of stuff, transforming this kind of stuff, this one is oppositely something. What did we say these ones are doing, guys? I forgot the term. Ish. What happened there?
Vertical opposite.
So
They are physical opposites.
yeah, all right. So yeah, we found the angles. Now let's find the electric field. Due to this N1, I'll call this N1, this one N2, this one N3, and that one N4. So due to 1, we will say flux is equal to EA cos theta, and this is our value. And then due to 2, we will say flux of the electric field is equals to EA, EA, which one is 2? This one. It is also EA cos theta. But we need to define which one is positive. Our electric field is moving this way, so N1 has to be negative because our theta is going to be, in fact, it's not our theta, it's our normal. Our normal and our electric field are not in the same direction, even though it is in terms of components because of the angle, but they are not in the same direction. But this one for 2 is positive because they are in the same direction. As we can see, N2 and this one, if you break this electric field into components, there's a component of the electric field in the direction of N2. What about 3?
That's right.
Yeah.
When we are writing for the equation for what is it? Is it for 2, for N2?
Yeah.
You're going to say EA, the cos of negative theta, right?
Yeah, you brought something very important. Let's see. Is it going to be negative theta? Why? Why negative theta?
Yes.
It's not negative. Remember, N2 is this one. These ones are vertically opposite. The angle is the same. What differs is that the normal is now backwards.
Okay. Sure. Isn't okay, if I say cos 180 plus theta, will I be wrong?
Cos 180 plus theta. I'm gonna have to do some maths to figure that one out.
Because in the previous one, we said the ones that are going in the opposite direction,
Yeah.
we are writing cos theta, right?
Yeah.
I don't know.
So what's cos 180? Negative. What's sin 180? 0. So we get negative cos theta if it's... Guys, do you all agree that cos 180 is 0? I mean, it's negative. Negative 1. Yeah. Yeah, if it's 180 plus theta, it's going to be negative. So why are you saying cos negative? Why are you adding 180? Are you saying we shouldn't use... We shouldn't use... Why did we use that we shouldn't use? I think I get your point. Yeah, you want us to not use this vertically opposite thing that we used, but instead we should add 180 so that we transform to this part. Is that right?
Yes, it is.
Okay, but then Your understanding, I like your understanding. It also makes sense to me. But in terms of the electric flux, it doesn't make sense for the electric flux to be negative when both angles are in the same direction. I think that's the only issue here. The electric field and the area vector are in the same direction, so it can't be negative. It has to be positive. It's negative if the electric field is now moving uh, in the opposite direction to our electric field. In fact, every time when you use the cosine angle, even when you calculate at work, remember, if you are moving forward and the force is backwards, the force has to be negative in this case. So the same thing applies here. The component of our area and the component of the electric field in the direction of our area, they are in the same direction, not in opposite directions like here. That's the only issue. Do you understand why now?
Yes, sir.
Alright. This marks our end of our session. We are left with 2 minutes. We will finish it in our next session. It's a small problem. Thank you for being with me today. It was a lovely lesson.